In modern software development, containers have become a standard, and many big companies are moving towards containers. So learning about them, how to use them in real projects will give you an advantage as a DevOps engineer in today's workplace. So in this module, you will learn all about containers and one of the most popular container technologies, which is Docker. To give you an overview, let's quickly go through the topics I will cover in this module. We will start with the fundamental concepts of what containers and Docker actually is and what problems they solve. We will also understand the difference between Docker and virtual machine. And after you have installed Docker, we will go through all the main Docker commands to start different applications as containers, debug those application containers, etc. We'll see how to use Docker in practice by going through a complete workflow with a demo project. First, how to develop with containers, running multiple containers and services with Docker Compose, building our own Docker image with Dockerfile, and pushing our built image into a private Docker repository. And finally, deploying and running our containerized application. As a final step of the demo project, we will look at how to persist data in Docker, learning the different volume types, and afterwards configuring persistence for our demo project. After that, based on the knowledge from the previous module about Nexus Repository Manager, we will see how to use Docker and Nexus in combination. So we will deploy and set up Nexus as a Docker container, as well as create our private Docker repository on Nexus and push and fetch our Docker images to that repository. So as you can imagine, by the end of this module, you will have a deep understanding about containers and a great overall picture of how Docker is used in the whole software development and application deployment process. And what's more important, you'll have hands-on experience in how to use all of this in practice. So we'll talk about what a container is and what problems it solves. We will also look at a container repository, which is basically a storage for containers. We'll see how a container can actually make the development process much easier and more efficient, and also how they solve some of the problems that we have in the deployment process of applications. So let's dive right into it, what a container is. A container is a way to package applications with everything they need inside of that package, including the dependencies and all the configuration necessary. And that package is portable, just like any other artifact is. And that package can be easily shared and moved around between a development team or development and operations team. And that portability of containers plus everything packaged in one isolated environment gives it some of the advantages that makes development and deployment process more efficient. And we'll see some of the examples of how that works in later slides. So as I mentioned, containers are portable, so there must be some kind of a storage for those containers so that you can share them and move them around. So containers live in a container repository. This is a special type of storage for containers. Many companies have their own private repositories where they host or where they store all the containers, and this will look something like this, where you can push all of the containers that you have. But there is also a public repository for Docker containers where you can browse and probably find any application container that you want. So let's head over to the browser and see how that looks like. So if I here search for a Docker Hub, which is the name of the public repository for Docker, I will see this official website. So here, if you scroll down, you see that there are more than 100,000 container images of different applications hosted or stored in this Docker repository. So here you see just some of the examples, and for every application there's this official Docker container or Docker container image. But if you're looking for something else, you can search it here, and I see there's an official image for, let's say, Jenkins, but there's also a lot of non-official images or container images that developers or or even from Jenkins itself, they actually store it here. So public repository is where you usually get started when you're using or when you're starting to use the containers, where you can find any application image. So now let's see how containers improve the development process by specific examples. How did we develop applications before the containers? Usually, when you have a team of developers working on some application, you would have to install most of the services on your operating system directly, right? For example, you are developing some JavaScript application and you need a PostgreSQL and you need Redis for messaging, and every developer in the team would then have to go and install the binaries of those services and configure them and run them on their local development environment. And depending on which operating system they're using, the installation process will look actually different. Also, another thing with installing services like this is that you have multiple steps of installation. So you have a couple of commands that you have to execute, and the chances of something going wrong and error happening is actually pretty high because of the number of steps required to install each service. And this approach, or this process of setting up a new environment, can actually be pretty tedious depending on how complex your application is. For example, if you have 10 services that your application is using, then you would have to do that 10 times on each operating system environment. So now let's see how containers solve some of these problems. With containers, you actually do not have to install any of the services directly on your operating system, because the container is its own isolated operating system layer with Linux-based image, as we saw in the previous slides. You have everything packaged in one isolated environment. So you have the PostgreSQL with a specific version packaged with the configuration and the start script inside of one container. So as a developer, you don't have to go and look for the binaries to download on your machine, but rather you just go ahead and check out the container repository to find that specific container and download on your local machine. And the download step is just one Docker command which fetches the container and starts it at the same time. And regardless of which operating system you're on, the Docker command for starting the container will not be different. It will be exactly the same. So if you have 10 applications that your JavaScript application uses and depends on, you would just have to run 10 Docker commands for each container, and that will be it. Which makes the setting up your local development environment actually much easier and much more efficient than the previous version. Also, as we saw in the demonstration before, you can actually have different versions of the same application running on your local environment without having any conflict. So now let's see how containers can improve the deployment process. Before the containers, a traditional deployment process will look like this. Development team will produce artifacts together with a set of instructions of how to actually install and configure those artifacts on the server. So you would have a jar file or something similar for your application, and in addition you would have some kind of a database service or some other service also with a set of instructions of how to configure and set it up on the server. So development team would give those artifacts over to the operations team, and the operations team will handle setting up the environment to deploy those applications. Now, the problem with this kind of approach is that, first of all, you need to configure everything and install everything directly on the operating system, which we saw in the previous example that could actually lead to conflicts with dependency versions and multiple services running on the same host. Another problem that could arise from this kind of process is when there is misunderstanding between the development team and operations, because everything is in a textual guide as instructions. So there could be cases where developers forget to mention some important point about configuration. Or maybe when operations team misinterpret some of those instructions. And when that fails, the operations team has to go back to the developers and ask for more details, and this could lead to some back and forth communication until the application is successfully deployed on the server. With containers, this process is actually simplified because now you have the developers and operations working in one team to package the whole configuration, dependencies inside the application, just as we saw previously. And since it's already encapsulated in one single environment, and you don't have to configure any of this directly on the server. So the only thing you need to do is run a Docker command that pulls that container image that you've stored somewhere in the repository and then run it. This is of course a simplified version, but that makes exactly the problem that we saw on the previous slide much more easier. No environmental configuration needed on the server. The only thing, of course, you need to do is you have to install and set up the Docker runtime on the server before you will be able to run containers there. But that's just one-time effort. So as you saw, I used Docker as an example to explain the concepts of containers. However, it's important to note here that Docker is just one of the implementations of containers, one of the most popular ones. Some other popular container technologies are Containerd, CRY-O, etc. Now that you know what a container concept is, let's look at what a container is technically. So technically, a container is made up of images. So we have layers of stacked images on top of each other, and at the base of most of the containers you would have a Linux-based image, which is either Alpine with a specific version, or it could be some other Linux distribution. And it's important for those base images to be small. That's why most of them are actually Alpine, because that will make sure that the containers stay small in size, which is one of the advantages of using a container. So on top of the base image, you would have application image. And this is a simplified diagram. Usually you would have these intermediate images that will lead up to the actual application image that is going to run in the container. And of course, on top of that, you will have all this configuration data. So now I think it's time to dive into a practical example of how you can actually use a Docker container and how it looks like when you install it and download it and run it on your local machine. So to give you a bit of an idea of how this works, let's head over to Docker Hub and search for PostgreSQL. So here, which is a Docker official image, I can see some of the versions, and let's say I'm looking specifically for older version, I don't know, 9.6 something. So I'm going to pull that one. So this is a Docker repository so that I can actually go ahead and pull the containers from that repository directly. And because it's a public repository, I don't have to log into it. I don't have to provide any authentication credentials or anything. I can just get started with a simple Docker command without doing or configuring anything to access Docker Hub. So on my terminal, I can just do Docker pull. I can even do Docker run and then just copy the image name. And if I don't specify any version, it will just give me the latest, but I want a specific version. So I'm gonna go with 9.6 actually, just to demonstrate. So I can provide the version like this with a colon, and I can start run. So as you see, the first line says unable to find image locally. So it knows that it has to go to Docker Hub and pull it from there. And the next line says pulling from library Postgres. And here you see a lot of hashes that says downloading. And this is what I mentioned earlier, which is Docker containers or any containers are made up of layers, right? You have the Linux image layer, you have the application layers, and so on. So what you see here are actually all those layers that are separately downloading from the Docker Hub on my machine, right? And the advantage of splitting those applications in layers is that actually, for example, if the image changes or I have to download a newer version of Postgres, what happens is that the layers, they're the same between those two applications. Two versions of Postgres will not be downloaded again, but only those layers that are different. So for example, now it's gonna take around 10 or 15 minutes to download this one image because I don't have any Postgres locally. But if I were to download the next version, it will take a little bit less time because some layers already exist on my local machine. So now you see that it's already logging because this command that I ran here, the docker run with the container name and version, it fetches or it pulls the container, but it also starts it. So it executes the start script right away as soon as it downloads it. And here you see the output of the starting of the application. So it just gives some output about starting the server and doing some configuration stuff. And here you see database system is ready to accept connections and launcher started. So now let's open the new tab and see with docker ps command you can actually see all the running containers. So here you see that Postgres 9.6 is running and it actually says image. So this is another important thing to understand when we're talking about containers. There are two technical terms, image and a container. And a lot of people confuse those two, I think. And there is actually a very easy distinction between the two. So image is the actual package that we saw in one of those previous slides. So the application package together with the configuration and the dependencies and all these things. This is actually the artifact that is movable around is actually the image. Container is when I pull that image on my local machine and I actually start it. So the application inside actually starts. That creates the container environment. So if it's not running, basically it's an image, it's just an artifact that's lying around. If I start it and actually run it on my machine, it is a container. So that is the distinction. So here it says the active running containers with a container ID, image that it's running from, and some entry commands that it executed and some other status information. So this means that PostgreSQL is now running on my local machine. Simple as that. If I were now to need, let's say, another version of Postgres to run at the same time on my local machine, I could just go ahead and say, let's go back, and let's say I want to have 9.6 and 10.10 running at the same time on my local machine. I would just do run Postgres and run. Again, it doesn't find it locally, so it pushes. And this is what I actually explained to you earlier, because it's the same application but with just a different version. Some of the layers of the image are the same, so I don't have to fetch those again because they are already on my machine, and it just fetches the layers that are different. So that saves a little bit of time, and I think it could be actually a good advantage. So now we'll wait for other image layers to load so that we have the second Postgres version running. And now you see I have Postgres 9.6 running in this command line tab, and I have Postgres version 10.10 running in the next one. So I have two Postgreses with different versions running, and I can actually output them here, have both of them running, and there's no conflict between those two. Like, I can actually run any number of applications with different versions maybe of the same application with no problem at all. And we're gonna go through how to use those containers in your application and the port configuration and some of the other configuration stuff later in this tutorial when we do a deep dive. But this is just for you to get the first visual image of how Docker containers actually work, how they look like, and how easily you can actually start them on your local machine without having to implement a specific version of Postgres application and do all the configuration yourself. When I first started learning Docker, after understanding some of the main concepts, my first question was, okay, so what is the difference between Docker and an Oracle VirtualBox, for example? And the difference is quite simple, I think. And in this short video, I'm going to cover exactly that. And I'm going to show you the difference by explaining how Docker works on an operating system level and then comparing it to how virtual machine works. So let's get started. In order to understand how Docker works on the operating system level, let's first look at how operating system is made up. So operating systems have two layers: operating system kernel and the applications layer. So as you see in this diagram, the kernel is the part that communicates with the hardware components like CPU and memory, etc. And the applications run on the kernel layer. So they are based on the kernel. So for example, you all know Linux operating system, and there are lots of distributions of Linux out there. There's Ubuntu and Debian, and there's Linux Mint, etc. There are hundreds of distributions. They all look different, so the graphical user interface is different, the file system is maybe different. So a lot of applications that you use are different because even though they use the same Linux kernel, they use different, or they implement different applications on top of the kernel. So as you know, Docker and virtual machine, they're both virtualization tools. So the question here is, what parts of the operating system they virtualize? So Docker virtualizes the applications layer. So when you download a Docker image, it actually contains the applications layer of the operating system and some other applications installed on top of it. And it uses the kernel of the host because it doesn't have its own kernel. The VirtualBox, or the virtual machine, on the other hand, has the applications layer and its own kernel. So it virtualizes the complete operating system, which means that when you download a virtual machine image on your host, it doesn't use your host kernel, it boots up its own. So what does this difference between Docker and virtual machine actually mean? So first of all, the size of Docker images are much smaller because they just have to implement one layer. So Docker images are usually a couple of megabytes. Virtual machine images, on the other hand, can be a couple of gigabytes large. A second one is the speed. So you can run and start Docker containers much faster than the VMs because every time you start them, they have to boot the operating system kernel and the applications on top of it. The third difference is compatibility. So you can run a virtual machine image of any operating system on any other operating system host, but you can't do that with Docker. So what is the problem exactly? Let's say you have a Windows operating system with a kernel and some applications, and you want to run a Linux-based Docker image on that Windows host. The problem here is that a Linux-based Docker image might not be compatible with the Windows kernel. And this is actually true for the Windows versions below 10 and also for the older Mac versions, which, if you have seen how to install Docker on different operating systems, you see that the first step is to check whether your host can actually run Docker natively, which basically means is the kernel compatible with the Docker images. So in that case, a workaround is that you install a technology called Docker Toolbox, which abstracts away the kernel to make it possible for your host to run different Docker images. So in this part, we're going to explain Docker a little bit more detail. As I mentioned, Docker is just one of the container tools. And even though containers have existed before Docker, Docker was one that made containers popular by making containers very user-friendly and easily usable. So how does Docker actually work? When you install Docker, you actually install something called a Docker engine, which comes with 3 parts. Docker server, which is the part that is responsible for pulling images, storing them, starting containers, stopping containers, and so on. Then you have Docker API, which is a part or API for interacting with the Docker server. And then you have a third part, which is the command line interface of Docker, which is a very powerful client to execute Docker commands against the server, to tell Docker server to pull images, run and stop containers, and so on. And Docker server itself has some main parts, which are container runtime, which is the one actually responsible for pulling the images, starting containers, stopping containers. So basically for container lifecycle. Then we have volumes functionality, which is responsible for persisting data in containers. The network part for configuring on Docker network for containers. And finally, a functionality to build our own Docker images. These are the actual artifacts that we can create from our applications to then run as Docker containers. And it's important to note that Docker is very powerful since it gives you all of these functionalities and more in one application. However, there are alternatives for parts of these functionalities, like there are container runtime tools like Containerd and CRY-O, for example, that you can use if you only need a container runtime on a server to run images, including Docker images. There are also tools that allow you to only build container images like Buildah, for example. So keep that in mind when thinking about alternatives to Docker. So in this section, we will be working with Docker. So you first need to install Docker locally on your computer. And in Docker official documentation, you can find guides to how to install it on your specific operating system, whether you're using Mac or Linux or Windows. Just note that Linux supports Docker natively, while for Windows and Mac, you need to install Docker Desktop. As always, you can find all the relevant links in the module checklist. So in this video, I'm going to show you some basic Docker commands. At the beginning, I'm going to explain what the difference between container and image is, because that's something a lot of people confuse. Then very quickly go through version and tag, and then show you a demo of how to use the basic Docker commands. Commands that will be enough to pull an image locally, to start a container, to configure a container, and even debug the container. So with that said, let's get started. So what is the difference between container and image? Mostly people use those terms interchangeably, but actually there is a fine difference between the two. To see theoretically, container is just a part of a container runtime. So container is the running environment for an image. So as you see in this graphic, the application image that runs the application, it could be Postgres, Redis, some other application, needs, let's say, a file system where it can save the log files or where it can store some configuration files. It also needs some environmental configuration like environmental variables and so on. So all of this environmental stuff are provided by container. And container also has a port that is binded to it, which makes it possible to talk to the application which is running inside of a container. And of course, it should be noted here that the file system is virtual in container. So the container has its own abstraction of an operating system, including the file system and the environment, which is of course different from the file system and environment of the host machine. So in order to see the difference between container and image in action, let's head over to the Docker Hub and find, for example, a Redis image. Another thing is that Docker Hub, all the artifacts that are in the Docker Hub are images. So we're not talking about containers here. All of these things are images, Docker official image. So we're going to go ahead and pull a Redis image out of the Docker Hub to my laptop. So you see the different layers of the image are downloaded. And this will take a couple of minutes. So once the download is complete, I can check all the existing images on my laptop using Docker images command. So I see I have 2 images, Redis and Postgres, with text, image IDs, and so on. Another important aspect of images is that they have tags or versions. So for example, if we go back to the Docker Hub, each image that you look up in the Docker Hub will have many different versions. The latest is always the one that you get when you don't specify the version, of course. If you have a dependency on a specific version, you can actually choose the version you want and specify it. And you can select one from here. So this is what you see here. The tag is basically the version of the image. So I just downloaded the latest, and I can also see the size of the image. So now to this point, we have only worked with images. There is no container involved and there is no Redis running. So now if, let's say I need Redis running so that my application can connect to it, I'll have to create a container of that Redis image that will make it possible to connect to the Redis application. And I can do it by running the Redis image. So if I say docker run Redis, this will actually start the image in a container. So as I said before, container is a running environment of an image. So now if I open a new tab and do docker ps, I will get status of all the running Docker containers. So I can see the container Redis is running with a container ID based on the image of Redis and some other information about it. For example, the port that it's running on and so on. So as you see here, the docker run Redis command will start the Redis container in the terminal in an attached mode. So for example, if I were to terminate this with the Control C, you see that Redis application stops and the container will be stopped as well. So if I do docker ps again, I see that no container is running. So there is an option for docker run command that makes it possible to run the container in a detached mode, and that is -d. So if I do docker run -d Redis, I will just get the ID of the container as an output, and the container will stop running. So if we check again docker ps, I see the container with the ID starting with 838, which is the same thing here, is running. So this is how you can start it in the detached mode. Now, for example, if you would want to restart a container because, I don't know, the application crashed inside or some error happened, so you want to restart it, you would need the container ID. So just the first part of it, not the whole string. And you can simply say docker stop ID of the container, and that will stop the Docker container. Nothing running. If you want to start it again, you can use the same ID to start again. So let's say you stop Docker container at the end of the day. You go home, you come back the next day, open your laptop, and you want to restart the stopped container, right? So if you do docker ps, the output is empty, you don't see any containers. So what you can do, alternative to just looking up your history, command line history, is you can do docker ps -a, which will show you all the containers which are running or not running. So here you see the container ID again, and you can restart it. Okay, so let's try another thing. Let's say you have two parallel applications that both use Redis but in different versions. So you would need two Redis containers with different image versions running on your laptop, right? At different times maybe, or at the same time. So here we have the latest one, which is Redis 5.06. And let's head over to the Docker Hub and select version. Let's say you need version 4.0. So remember the first time that we downloaded the Redis image, we did docker pull Redis. However, if you use docker run with Redis image and the tag, which was 4.0, it will pull the image and start the container right away after it. So it does two commands basically in one. So it's docker pull, then docker start in one command. So if I do this, it says it can't find the image locally. So it goes and pulls the image from the repository to my laptop. And again, we see some layers are downloaded and the container is started right away. And now if I do docker ps, you see that I have two Redises running. So this is where it gets interesting. Now, how do you actually use any container that you just started? So in this output, you also see the ports section, which specifies on which port the container is listening to the incoming requests. So both containers open the same port, which is what was specified in the image. So in the logs of the container, you can see the information, running mode, standalone, port 6379. So how does that actually work? And how do we not have conflicts while both are running on the same port? So to explain that, let's head over to our slide and see how this works. As you know, container is just a virtual environment running on your host. And you can have multiple containers running simultaneously on your host, which is your laptop, PC, whatever you're working on. And your laptop has certain ports available that you can open for certain applications. So how it works is that you need to create a so-called binding between a port that your laptop, your host machine has, and the container. So for example, in the first container part here, you see container is listening on port 5000 and you bind your laptop's port 5000 to that containers. Now, you will have conflict if you open two 5000 ports on your host, because you will get a message, the port is already bound or is already in use. You can do that. However, you can have two containers, as you see, the second and third containers are both listening on port 3000, which is absolutely okay as long as you bind them to two different ports from your host machine. So once the port binding between the host and the container is already done, you can actually connect to the running container using the port of the host. So in this example URI, you would have some app, localhost, and then the port of the host. And the host then will know how to forward the request to the container using the port binding. So if we head back, here you see that containers have their ports and they're both running on the same one. However, we haven't made any binding between my laptop's port and the container port. And because of that, the container is basically unreachable by any application, so I won't be able to use it. So the way we actually do that is by specifying the binding of the ports during the run command. So I'm gonna break this and check that there is just one container running now. I'm gonna stop the other one as well so we can start them anew. Okay, so we see both containers are here. So now we want to start them using the binding between the host and the container ports. But again, we have two Redises, so we need to bind them to two different ports on my laptop. So the way to do it is you do docker run and you specify with -p the port of the host. That's the first one. So let's go with 6000. It doesn't really matter in this case. And the second one is the port that you're binding this to, which is the container port. So we know the container port will be 6379, and this is where we bind my laptop's port 6002. And if I do this, I forgot Redis here. So, and now if I do docker ps, let's actually clean this, docker ps again. Here you see the binding here, right? So your laptop's 6000 port is bound to the containers 6379. So now let's do another thing and let's start it in a detached mode. So like this. Let's check again. It's running again. And now I want to start the second container. Let's clear this again. So here you see it created a bunch of containers because when I specified different options with the port binding, it actually created new containers. That's why you see a couple of more here. So I'm gonna copy the image name with the tag for .o -p. So for example, if I were to do this now, and I would try to run the other Redis, the second Redis container with the same port on my laptop, I would get an error saying port is already allocated. So I can do 6001 and run it. Again, I'll run it in detached mode so that I don't see port. And if I go over here and say docker ps, I see that I have two different Redis versions running, both of them bound to different ports on my laptop, and the containers themselves listening to requests on the same port. So far we have seen a couple of basic Docker commands. We have seen docker pull, which pulls the image from the repository to local environment. We also saw run, which basically combines docker pull and docker start, pulls the image if it's not locally available and then starts it right away. Then we saw docker start and docker stop, which makes it possible to restart a container if you made some changes and you want to create a new version, which makes it possible to restart a container if you need to. We also saw docker run with options. The one option that we saw was -d, which is detach. So you can run the container in detached mode, so you can use terminal again. -p allows you to bind port of your host to the container. So very important to remember -p, then comes the port of your host, and then comes the port of your container, whatever it might be. We also saw docker ps -a, which basically gives you all the containers, no matter if they're running currently or not. We also saw docker images, which gives you all the images that you have locally. So for example, if after a couple of months you decide to clean up your space and get rid of some stale images, you can actually check them, check the list, and then go through them and delete them. You can do the same with stale Docker containers that you don't use anymore or you don't need anymore. You can also get rid of them. So the final part of the Docker basic commands are commands for troubleshooting, which are very, very useful. If something goes wrong in the container, you want to see the logs of the container, or you want to actually get inside of container, get the terminal and execute some commands on it. So let's see Docker PS. We have 2 containers running, right? Now, we don't have any output, we don't see any logs here. So let's say something happens, your application cannot connect to Redis and you don't know what's happening. So ideally, you would want to see what logs Redis container is producing, right? The way to do that is very easy. You just say docker logs and you specify the container ID and you see the logs. You can also do the docker logs if you don't want to remember the container ID or do Docker PS all the time. You can remember the name of the container and you can get the logs using the name. So a little side note here, as we're talking about the names of the containers. So here, as you see, when a container is created, you just get some random name like this. So you can name your containers as you want using another option of the Docker run, which might be pretty useful sometimes if you don't want to work with the container IDs and you just want to remember the names, or if you just want to differentiate between the containers. So for example, let's create a new container from Redis 4.0 image using a different name that we choose. So I'm gonna stop this container and I'm going to create a new one from the same image. So let's run it in the detached mode. Let's open the port 1001 to 6379 and give the name to the container. And let's call, since it's the older version, let's call it Redis older. And we need to specify the image. So remember, this will create a new container since we're running the docker run command again. So if we execute this and check again, we see the Redis 4.0 image based container is created, which is fresh new. You can see in the created, and the name is Redis older. And we can do the same for the other container so that we kind of know which container is what. So I'll stop this one and I will use the same command here. This will be the latest and I will call this Redis latest. And since bind another port, so I'm gonna run it and let's see. So here I have 2 containers running. Now I know Redis older, Redis latest. So for example, if the older version has some problems, I can just do logs Redis older and I can get my logs. So another very useful command in debugging is docker exec. So what we can do with docker exec is we can actually get the terminal of a running container. So let's check again. We have 2 containers running and let's say there is some problem with the latest Redis latest container and I want to get a terminal of that container and to maybe navigate a directory inside, check the log file, or maybe check the configuration file, or print out the environmental variables, whatever. So in order to do that, we use docker exec command with -t, which stands for interactive terminal. Then I specify the container ID and I say in bash. So I get the bash. And here you see that the cursor changed. So I'm inside of the container as a root user. And here, if I say ls, okay, the date is empty. I can also print out in which directory I am. I can go to the home directory, see what's there. So I have my virtual file system inside of a container. And here I can navigate the different directories and I can check stuff. I can also print all the environmental variables to see that something is set correctly and do all kinds of stuff here. And this could be really useful if you have a container with some complex configuration, or if, for example, you are running your own application that you wrote in a container and you have some complex configuration there or some kind of setup, and you want to validate that everything is correctly set. In order to exit the terminal, you just do exit and you're out. You can also do the same using the name. Again, if you don't want to work with the IDs and you just want to remember the names of the container to make it easier, you can do it with the name as well. Same thing. Since most of the container images are based on some lightweight Linux distributions, you wouldn't have much of the Linux commands or applications installed here. For example, you wouldn't have curl or some other stuff. So you are a little bit more limited in that sense. So you can't execute a lot of stuff from the Docker containers. For most of the debugging work, it should be actually enough. So the final part to review the difference between Docker run and Docker start, which might be confusing for some people. Let's revisit them. So basically Docker run is where you create a new container from an image. So Docker run will take an image with a specific version or just latest, right, as option or as an attribute. With Docker start, you're not working with images, but rather with containers. So for example, as we saw, Docker run has a lot of options. You specify with -d and -p, the port binding, and then you have this name of the container and all this stuff. So basically you tell Docker at the beginning what kind of container with what attributes, name, and so on to create from a specific image. But once the container is created, and you can see that using the command. So for example, here, the last ones that we created. And if you stop it and you want to restart it, you just need to use the command docker start and specify the container ID. And when you start it, the container will retain all the attributes that we defined when creating the container using Docker run. So Docker run is to create a new container. Docker start is to restart a stopped container. So once you've learned the Docker basic concepts and understood how it works, it's important to see how Docker is actually used in practice. So in software development workflow, you will know you have these classical steps of development, and you have continuous delivery or continuous integration, and then eventually it gets deployed on some environment, right? It could be a test environment, develop environment. So it's important to see how Docker actually integrates in all of those steps. So in the next couple of videos, I'm going to concentrate exactly on that. So we're going to see some overview of the flow, and then we're going to zoom in on different parts and see how Docker is actually used in those individual steps. So let's consider a simplified scenario where you are developing a JavaScript application on your laptop, right? On your local development environment. Your JavaScript application uses a MongoDB database, and instead of installing it on your laptop, you download a Docker container from the Docker Hub. So you connect your JavaScript application with the MongoDB and you start developing. So now let's say you develop the application, first version of the application locally, and now you want to test it, or you want to deploy it on the development environment where a tester in your team is gonna test it. So you commit your JavaScript application in Git or in some other version control system. That will trigger a continuous integration, a Jenkins build, or whatever you have configured. And Jenkins build will produce artifacts from your application. So first, it will build your JavaScript application and then create a Docker image out of that JavaScript artifact, right? So what happens to this Docker image once it gets created by Jenkins build? It gets pushed to a private Docker repository. So usually in a company, you would have a private repository because you don't want other people to have access to your images. So you push it there. And now, as a next step, could be configured on Jenkins or some other scripts or tools. That Docker image has to be deployed on a development server. So you have a development server that pulls the image from the private repository, your JavaScript application image, and then pulls the MongoDB that your JavaScript application depends on from a Docker Hub. And now you have two containers, one your custom container and a publicly available MongoDB container running on dev server. And they talk to each other. You have to configure it, of course. They talk and communicate to each other and run as an app. So now if a tester, for example, or another developer logs in to a dev server, they will be able to test the application. So this is a simplified workflow, how Docker will work in a real-life development process. In the next videos, I'm going to show you a hands-on demo of how to actually do all of this in practice. So in this video, we are going to look at some practical example of how to use Docker in a local development process. So what we're going to do is a simple demo of a JavaScript and Node.js application in the backend to simulate the local development process. And then we're going to connect it to a Docker container with a MongoDB database in it. So let's get started. So in this video, we're going to see how to work with Docker containers when developing applications. So the first step will be we're going to develop a very simple UI backend application using JavaScript, very simple HTML structure and Node.js in the backend. And in order to integrate all of this in the database, we are going to use a Docker container of a MongoDB database, and also to make working with the MongoDB much easier, so we don't have to execute commands in the terminal. We're going to deploy a Docker container of a Mongo UI, which is called the Mongo Express, where we can see the database structure and all the updates that our application is making in the database. So this development setup should give you an idea of how Docker containers are actually used in the development process. So I've already prepared some very simple JavaScript application. So in order to see the code, basically we have this index.html that is very simple code, and we have some JavaScript here, and we're using Node.js backend that just serves that index.html file and listens on port 3000. So we have the server running here in the backend, and we have the UI that looks like this. So basically it's just the user profile page with some user information, and user can edit their profile. So if I, for example, change the name here, and if I change the email address and do changes like this, I can save my profile and I have my updates here. However, if I refresh the page, of course, the changes will be lost because it's just JavaScript Node.js. So there is no persistent component in this application. So in order to have that, which is actually how real life applications work, you'll know that you need to integrate the application with a database. So using that example, I will try to showcase you how you can actually use the Docker containers to make the development process easier by just pulling one of the databases and attaching it or connecting it to the application. So in this case, we're going to go with the MongoDB application. And in addition to MongoDB container, we're going to also deploy a MongoDB UI, which is its own container. It's called Mongo Express, where we can manage or see the database insights and updates from our application much easier. So now let's see how that all works. So in order to get started, let's go to Docker Hub and find our MongoDB image. So here, let's go to Mongo. And we have MongoDB here. Actually, and the Mongo Express, which is another Docker container that we're going to use for the UI. So first, let's pull the MongoDB official image. So I already have MongoDB latest, so pulling doesn't take longer on my laptop, but you're gonna need a couple of seconds probably. And the next one we're gonna pull is the Docker Express, which I also have, I believe. So let's see. Yes, it's also fast. So if I check locally, I have MongoDB and Mongo Express images. So the next step is to run both Mongo and Mongo Express containers in order to make the MongoDB database available for our application, and also to connect the Mongo Express with the MongoDB container. So let's do the connection between those two first. In order to do that, we have to understand another Docker concept, Docker network. So how it works is that Docker creates its isolated Docker network where the containers are running in. So when I deploy two containers in the same Docker network, in this case Mongo and Mongo Express, they can talk to each other using just the container name, without localhost, port number, etc., just the container name, because they're in the same network. And the applications that run outside of Docker, like our Node.js, which just runs from Node server, is going to connect to them from outside or from the host using localhost and the port number. So later, when we package our application into its own Docker image, what we're going to have is, again, a Docker network with MongoDB container, Mongo Express container, and we're going to have a Node.js application which we wrote, including the index.html and JavaScript for frontend in its own Docker container, and it's going to connect to the MongoDB. And the browser, which is running on the host but outside the Docker network, is going to connect to our JavaScript application, again using hostname and the port number. So Docker by default already provides some networks. So if we say Docker network ls, we can already see these auto-generated Docker networks. So we have 4 of them with different names and the drivers. We're not going to go into details here, but what we're going to do is create its own network for the MongoDB and the Mongo Express, and we're going to call it Mongo Network. So let's do this right away. I'm going to say Docker network create, and we are going to call it Mongo Network. So now if I do Docker network ls again, I see my Docker network has been created. So now in order to make our MongoDB container and the Mongo Express container run in this Mongo network, we have to provide this network option when we run the container in the Docker run command. So let's start with the Mongo. So we all know that Docker run is the command to start a container from an image, right? So we have Docker run Mongo, which is the basic Docker run command. However, in this case, we want to specify a couple of things. As you learned from the previous videos, you have to specify something called port. So we need to open a port of MongoDB. The default port of MongoDB is 27017. So we'll take that port actually for both host and container. So Mongo will run at this port inside of a container, and we open the same port on the host. So that will take care of the port. Then we will run it in a detached mode. In addition to that, there are a couple of things that we can specify when starting up the container. And these are environmental variables of the MongoDB. Let's see, in the official image description, you actually have a couple of documentation about how to use the image, which is very helpful to kind of understand what kind of configuration you can apply to it. Here you see some environmental variables. So basically on startup, you can define what the root username and the password will be, which is very handy because we're going to need those two for the Express to connect to the Mongo. And you can also specify the init database. We're just going to provide the username and password because we can create the database from the Mongo Express UI later. So let's do that. And the way you can specify the environmental variables, you can actually see here as well, is by just, let's copy this one. So here you say environmental variable, that's what the -e flag stands for. And root username, we'll say it's admin, and another variable, which is the password, will be just password. So in this way, we can actually override what the default username and password will be. So 2 more things that we need to configure in this command are container name, because we're gonna need that container name to connect with the Mongo Express. So we'll call this one MongoDB, let's say. And another one we need is the network that we created, which was called Mongo Network. So in order to make this command a little bit more structured, do it on multiple lines. So let's see. So it's more readable. So basically all these options or all these flags that we set, to go one more time through them, it's going to start in detached mode. We are opening the port on the host, username and password that we want MongoDB to use in the startup process. We're going to rewrite or overwrite the name of the container, and this container is going to run in a Mongo network. And this should actually start the container. Okay, so if you want to see whether it was successful, we can log the container and see what's happening inside. So as we see, Mongo was started and everything actually looks good. Waiting for connections on port 27017. Okay, so now let's start Mongo Express. We want Mongo Express to connect to the running MongoDB container on startup. And here we have an example of how to run it. And here we have the list of environmental variables that we can configure. So let's quickly look at them. Username, password, we don't need them. However, we need the admin username and admin password of the MongoDB. This is actually what we overrode with admin and password. So we're going to use them because Express will need some username password to authenticate with the MongoDB and to connect it. The port is by default the correct one, so we don't need to change that. And this is an important part. This is the MongoDB server, right? So basically this is the container name that Express will use to connect to the Docker. And because they are running in the same network, only because of that, this configuration will work. If I hadn't specified the network, then I could specify the correct name here of the container, but it wouldn't work. So with that said, let's actually create the Docker run command for Express as well. So let's clear the history and let's start. So again, we run it in detached mode and let's see what parameters we need. So first of all, port, let's say what is the default port that the Express runs on. That's 8081. So we'll take that. So basically it's going to run on our laptop on port 8081. The next option would be these two. And remember, environmental variables need to be specified with -e. And this is the username of MongoDB admin, which is admin, because we specified it when we started the MongoDB container. This is the password. Let's set this one as well. Don't forget the network, --net Mongo network. We have the name. We can also call it Mongo Express. And let's see what else we might need here. Yes, this is an important one. And our container name, let's actually see it again. Docker PS, the one running. It's called MongoDB. That's the container name, and this is what we need to specify here. So I'm going to write this here. And finally, the image is called Mongo Express. So I'm just going to copy this one here, and that is it. So basically with these commands, Mongo Express should be able to connect to the MongoDB container. So let's run it, and just to make sure, let's log the container and see what's happening there. Waiting for MongoDB. Welcome to Mongo Express. It looks like it connected successfully. It says here, database connected. And the Mongo Express is available at port 8081. So let's check the Mongo Express out at the port 8081. So actually let's close these tabs. We don't need them anymore. And here, if I say localhost 8081, I should be able to see the Mongo Express. So these are the databases that already exist by default in Mongo, or which are created on startup. And using the UI, we can create our own database. As we saw previously, we could have specified an environmental variable initDB on MongoDB startup, and that would have created a new database. However, it doesn't matter. We will just create a database name here. So we will call it user account database. So let's create one. And now we can actually use it or connect to this database from Node.js. So let's see how that works. So now we have the MongoDB container and the Mongo Express container running. So let's check that. We have both of them. We'll have to connect Node.js with the database. So the way to do it is usually to give a protocol of the database and the URI. And the URI for a MongoDB database would be localhost and the port that it's accessible at. I already went ahead and prepared the code for Node.js. So basically we are going to use a Mongo client here, which is a Node module. And using that Mongo client, we are connecting to the MongoDB database. So this is the protocol, the host, and the port that we just saw that the MongoDB is listening at, and username and password of the root user of MongoDB. Of course, usually you wouldn't put the password here or not use an admin or root username password to connect to a database, but this is for just the demonstration purposes. And these are username and password that we set as environmental variables when we created the Docker MongoDB container. So let's check that. So this is the MongoDB container command, and this is the username, root, and root password that we specified, and this is what we are gonna use in the code. As I said, for demonstration purposes, I will write the password directly here. So then we connect to the database. So I also went ahead and in the Mongo Express user account database, and inside that I created a collection, which is like a table in MySQL world called users. So here I connect to a user account database and I query the collection users. And this is a GET request, so I'm just fetching something from the database, and this is update request, same thing. I connect to the database using the same URI and the database name, and I update or insert something in the collection. So now let's see how all that works. So let's head over to the UI. So in the users collection, there is no data, it's empty. So we're gonna refresh it and edit the data. So I'm gonna write here some and update it and refresh. We see that a new insert was made. So this is the update profile section here. So all this was executed, it connected to the MongoDB, and now we have one entry, which is email, coding, name that we changed. So if I'm gonna refresh it now, I fetched the newly inserted user data in the UI and I displayed it here. And also if you wanna see what the MongoDB container actually logs during this process, we can actually look at the logs. So I'm gonna say docker ps and log using the container ID. So let's say if I wanted to see just the last part of it because I want to see what the last activity was, I can also, let's clear this, and I can also do tail, so I can just display the last part of it. Or if I wanted, I could also stream the logs. So I'll clear this again, and I'll say stream the logs. So I won't have to do Docker logs all the time. So if I make a line here, for example, to mark the last logs, I can refresh it. Let's make some other changes. Let's change it to bones and save profile. So I'm gonna see some activity here as well. So these connections are new, and it also says received client metadata, and this is where the Node.js request comes in with the Node.js and its version. And at the end of each communication, there is an end connection because we end the database connection at the end. So we see that also in the logs. So if, for example, something wasn't working properly, you could always check them in the logs here. So with that, I have a fully functional JavaScript Node.js application which has a persistence in the MongoDB database, and we also have Mongo UI, both of them running in a Docker container. So this would be somehow a realistic example of how local development using Docker containers would look like. So in the last video, we created and started two Docker containers, MongoDB and MongoExpress. And these are the commands that we used to make it happen, right? The first, we created a network where these two containers can talk to each other using just the container name, and no host, port, etc. is necessary for that. And then we actually ran two Docker run commands with all the options and environmental variables, etc. set. Now, this way of starting containers all the time is a little bit tedious, and you don't want to execute these run commands all the time on the command line terminal, especially if you have a bunch of Docker containers to run. You probably want to automate it or just make it a little bit easier. And there's a tool that makes running multiple Docker containers with all this configuration much easier than with Docker run commands, and that is Docker Compose. If you already know Docker Compose and you were wondering why is it useful and what it actually does, then bear with me. In the next slide, I'm going to explain that. So this is a Docker run command of the MongoDB that we executed previously. So basically, with Docker Compose file, what we can do is we can take the whole command with its configuration and map it into a file so that we have a structured commands. So if you have, let's say, 10 Docker containers that you want to run for your application, and they all need to talk to each other and interact with each other, you can basically write all the run commands for each container in a structured way in the Docker Compose. And we'll see how that structure actually looks like. So on the right side in the Docker Compose example, the first two tags are always there, right? Version 3, that's the latest version of the Compose, Docker Compose, and then we have the services. This is where the container list goes. So the first one is MongoDB, and that maps actually to the container name, right? This is going to be a part of container name when Docker creates a container out of this configuration blueprint. The next one is actually the image, right? So we need to know which image that container is going to be built from. And of course, you can specify a version tag here next to the name. The next one is port. So we can also specify which ports is going to open. First one is on the host, and the second one after the colon is on the container. So the port mapping is there. And of course, the environmental variables can be also mapped in the Docker Compose. And this is how actually the structure of Docker Compose looks like for one specific command. Let's actually see the second container command for MongoExpress that we executed and how to map that. So now again, we have a Docker run command for MongoExpress, and let's see how we can map it into a Docker Compose. So as I said, services will list the containers that we want to create. And again, names, MongoExpress will map to the container name. The next one will be the image. Again, you can add a tag here if you want to be have a specific one. Then you have the ports, 80 to 8080. And then you have all the environmental variables, again, under the attribute environment. And this is how the Docker Compose will look like. So basically, Docker Compose is just a structured way to contain very normal common Docker commands. And of course, it's going to be easier for you to edit the file if you want to change some variables, or if you want to change the ports, or if you want to add some new options to the run command, so to say. And maybe you already noticed the network configuration is not there in the Docker Compose. So this Mongo network that we created, we don't have to do it in a Docker Compose. If we go to the next slide, because we have the same concept here, we have containers that will talk to each other using just the container name. So what Docker Compose will do is actually take care of creating a common network for these containers. So we don't have to create the network and specify in which network these containers will run in. And we're going to see that in action right away. So let's actually create a Docker Compose file. So I'm going to paste all my contents here. And this is exactly what we saw on the slides. And I'm going to save it as a Mongo YAML. And we see the highlighting as well. Be very aware of the indentation. They have to be correct. So this is the list of all the containers on the same level. And then each container has its configuration inside that. So now, compared to Docker run commands, it will be very easy for me to go here and change these environment variables or add some new configuration options, etc. So here again for demonstration, we actually save the Docker Compose in the code. So it's part of the application code. So now that we have a Docker Compose file, the question is, how do I use it, or how do I start the containers using that? So let's go to the command line and start Docker containers using this Docker Compose file. So the way to use it is using Docker Compose command. Now, if you've installed Docker on your laptop, it usually gets installed with the Docker Compose packaged inside. So you should have both Docker and Docker Compose commands installed as a package. So Docker Compose command takes an argument, which is the file. So I'm going to specify which file I want to execute. And in my case, it's called Mongo YAML. And at the end, I want to say what I want to do with this file. In this case, the command is up, which will start all the containers which are in the Mongo YAML. So let's actually check before that there are no containers running. So I don't have anything running here. And I'm going to start those two containers. Okay, so there are a couple of interesting things here in this output. So let's scroll all the way up. So we've talked about Docker network and how we created our own network at the beginning to run the containers inside. And I said that Docker Compose takes care of it. And here we see the output where it actually created a network called myAppDefault. This is the name of the network. And it's gonna run those two containers. These are actually the names of the containers that Docker Compose created. This is what we specified. And it just added prefix and suffix to it. And it created those two containers in that network. So if I actually go here and do docker network ls, I see the myAppDefault is here. So that's one important thing. Another one is that logs of both containers actually mixed because we're starting both at the same time. As you see, the Mongo Express has to wait for MongoDB to start because it needs to establish a connection. So we here see the logs. So MongoDB is starting. We still get connection refused because it's not started completely. And somewhere here, when MongoDB is started and listening for connections, Mongo Express is able to connect to it. So this is something that you can also do with Docker Compose. When you have two containers where one depends on another one starting, you can actually configure this waiting logic in the Docker Compose. Okay, so now let's see actually that the Docker containers are running. So we have both of them. Here you see the container names that Docker Compose gave them. And one thing here to note is that the Mongo Express actually started on port 8081 inside the container. So we can see that here. So we are opening a port 8080 on my laptop that actually forwards the request to container at port 8081. Just so that you don't get confused because it was 8080 on the slides. So now that we have restarted the containers, let's actually check the first one, which is Mongo Express. So it's running on 8080. In the previous example, we created a database and a collection, which is gone because we restarted the container. This is actually another very important concept of containers to understand. When you restart a container, everything that you configured in that container's application is gone. So data is lost, so to say. There is no data persistence in the containers itself. Of course, that is very inconvenient. You want to have some persistence, especially when you're working with a database. And there is a concept we're going to learn later called volumes that makes it possible to have persistency between the container restarts. Okay, so let's actually create the database again because we need it. And inside the database, we had actually users collection. Let's create that one as well. And that is empty. Now let's actually start our application. And there you go. So now if I were to modify this one here and update, I should see the updated entry here. So the connectivity with MongoDB works. So now what do I do if I want to stop those containers? Of course, I could go there and say docker stop, and I can provide all the IDs as we did previously, or with Docker Compose, it's actually easier. I can do Docker Compose, again, specify the file, and instead of up, I'm gonna say down. And that will go through all the containers and shut them all. And in addition to removing the containers or stopping them removing the containers, it also removes the network. So the next time we restart it, it's gonna recreate. So let's actually check that. Docker network ls. That default, my app default network is gone. And when I do up, see, it gets recreated. That should give you a good idea of what Docker Compose is and how to use it. In the next video, we're gonna build our own Docker image from our Node.js JavaScript application. So now let's consider the following scenario. You have developed an application feature, you have tested it, and now you're ready to deploy it, right? To deploy it, your application should be packaged into its own Docker container. So this means that we're gonna build a Docker image from our JavaScript Node.js backend application and prepare it to be deployed on some environment. To review this diagram that we saw at the beginning of the tutorial, so we have developed a JavaScript application, we have used the MongoDB Docker container to use it, and now it's time to commit it to the Git. Right? So in this case, we're going to simulate this on the local environment, but still, I'm going to show you how these steps actually work. So after commit, you have a continuous integration that runs. So the question is, what does actually Jenkins do with this application? When it builds the application, so the JavaScript application using the npm build, etc., it packages it then in a Docker image. And then pushes it into a Docker repository. So we're going to actually simulate what Jenkins does with their application and how it actually packages it into a Docker image on the local environment. So I'm going to do all this on my laptop, but it's basically the same thing that Jenkins will do. And then on later step, we can actually push the built image into a Docker repository. In order to build a Docker image from an application, we basically have to copy the contents of that application into the Docker file. It could be an artifact that we built. In our case, we just have 3 files, so we're going to copy them directly in the image and we're going to configure it. And in order to do that, we're going to use a blueprint for building images, which is called a Docker file. So let's actually see what is a Docker file and how it actually looks like. So as I mentioned, Dockerfile is a blueprint for creating Docker images. A syntax of a Dockerfile is super simple. So the first line of every Dockerfile is from image. So whatever image you are building, you always want to base it on another image. In our case, we have a JavaScript application with Node.js backend, so we are gonna need Node inside of our container so that it can run our Node application, instead of basing it on a Linux Alpine or some other lower level image, because then we would have to install Node ourselves on it. So we are taking a ready Node image. And in order to see that, let's actually go to Docker Hub and search Node here. And here you see there is a ready Node image that we can base our own image from. So here we have a lot of different tags, so we can actually use one specific one, or we can just go with the latest if we don't specify any tag. So what that actually means, basing our own image on a Node image, is that we are gonna have Node installed inside of our image. So when we start a container and we actually get a terminal of the container, we can see that Node command is available because there's Node installed there. This is what from Node actually gives us. So the next one is we can configure environmental variables inside our Docker file. Now, as you know, we have already done this using the Docker run commands or the Docker compose. So this will be just an alternative to defining environmental variables in a Docker compose, for example. I would say it's better to define the environmental variables externally in a Docker compose file, because if something changes, you can actually override it. You can change the Docker compose file and override it instead of rebuilding the image. But this is an option. So this env command basically would translate to setting the environmental variables inside of the image environment. The next one is run. So all these capital case words that you see from env and run, they're basically part of a syntax of a Docker file. So using run, basically you can execute any kind of Linux commands. So you see make directory is a Linux command that creates a home/home/app directory. Very important to note here. This directory is gonna live inside of a container. So when I start a container from this image, the /home/app directory will be created inside of the container and not on my laptop, not on the host. So all these commands that you have in Dockerfile will apply to the container environment. None of them will be affecting my host environment or my laptop environment. So with run, basically you can execute any Linux commands that you want. So that's probably one of the most used ones. And we also have a copy command. Now you would probably ask, I can execute a copy command, a Linux copy command using run. Yes, you could, but the difference here is that, as I said, all these commands in run, for example, they get executed inside of the container. The copy command that you see here, it actually executes on the host. And you see the first parameter is dot, and the second parameter is /home/app. So source and the target. So I can copy files that I have on my host inside of that container image. Because if I were to execute run cp source destination, that command would execute inside of the Docker container. But I have the files that I want to copy on my host. And the last one, so from and cmd or command is always part of Dockerfile. What command does is basically executes an entry point Linux command. So this line with the command actually translates to node server.js. So remember here, we actually do node server.js. So we start a node server with the node.js. This is exactly what it does, but inside of the container. So once we copy our server.js and other files inside of a container, we can then execute node server.js. And we are able to do it because we are basing on the node image that already has node pre-installed. And we are gonna see all this in action. So another question here, what is the difference between run and cmd? Because I could also say run node server.js. The difference again is that cmd is an entry point command. So you can have multiple run commands with different Linux commands, but cmd is just one. And that marks for Dockerfile that this is the command that you want to execute as an entry point. So that basically runs the server and that's it. So now let's actually create the Dockerfile, and just like the Docker Compose file, Dockerfile is part of the application code. So I'm gonna create a new file here and I'm gonna paste here the contents. So again, we're basing off node image, and actually instead of just having the latest node, I'm gonna specify a node version. So I'm going to take 13 minus alpine. So all this that you see here are tags. So I can use any of them as a tag. So I'm gonna say 13 minus alpine like this. So this is gonna be a specific node image that I'm gonna use as my base image. Let's actually stop here for a moment and take a little bit of a deep dive on this line. So since we saw that Dockerfile is a blueprint for any Docker image, that should actually mean that every Docker image that there is on Docker Hub should be built on its own Dockerfile, right? So if we actually go to, let's actually look at one of the latest versions, which is 13 minus alpine, and then let's click inside. And as you see, this specific image has its own Dockerfile. And here, as you see, we have the same from that we just saw. And this is what this node official image is based off, which is a base image alpine 3.10, right? And then we have this environmental variable set and all these Linux commands using run and some other environmental variable. And you have this entry point, which is a script. So you can also execute the whole shell script instead of separate commands. And you have this final command, right? So you don't have to understand any of this. I just want to demonstrate that every image is based off another base image, right? So in order to actually visually comprehend how this layer stacking works with images, let's consider this simplified visualization. So our own image that we're building, app with the version 1.0, is going to be based on a node image with a specific version. That's why we're going to specify from node 13 alpine. And the node 13 alpine image, as we saw in the Dockerfile, is based on alpine base image with the version 3.10. That's why it specifies from alpine 3.10. So alpine is a lightweight base image, then we install node on top of it, and then we install our own application on top of it. And basically this is how all the images are built. So now let's go back and complete our Dockerfile. So we have the from specified, we have the environmental variables specified, and in just a second we're gonna actually see these commands in action. So let's copy that, and this is also very important. Dockerfile has to be called exactly like that. You can't just give it any name. It is always called Dockerfile, starting with a capital D, and that's it. It's a simple text file, so just save it like this. And here you even see the highlighting and this Docker icon. So now that we have a Dockerfile ready, let's see how to actually use it. So how do we build an image out of it? So in order to build an image using a Dockerfile, we have to provide two parameters. One is we want to give our image a name and a tag, just like all the other images have. So we are going to do it using -t. So we're going to call our image my app, and we're going to give it a tag of 1.0. The tag could be anything. You can even call it actually version 1. It wouldn't matter. So we're going to do 1.0. And the second required parameter actually is a location of a Docker file, because we want to tell Docker, here, build an image using this Docker file. And in this case, because we're in the same folder as the Docker file, we're just going to say current directory. When we execute this, we're going to see that image is built. And this is an ID of the image that was built. Because I already have Node 13 Alpine on my laptop, this just use the one I have lying around locally. For you, if it's the first time, you will actually see that it's pulling Node image from the Docker Hub. So now with the Docker images, I can actually see that my image is here. So I have the image name, which is this one here, and I have the name of the image and the tag of the image. So if we go back to this diagram that we saw in the review, so basically we've gone all these steps, or we have simulated some of the steps. We've built the JavaScript application using a Docker containers. And once the application is ready, let's say we made the commit, and we just simulated what Jenkins server also does. So what Jenkins does is actually it takes the Docker file that we create. So we have to commit the Docker file into the repository with the code. And Jenkins will then build a Docker image based on the Docker file. And what is an important point here is that usually you don't develop alone, you are in the team. So other people might want to have access to that up-to-date image of your application that you developed. It could be a tester maybe who wants to pull that image and test it locally, or you want that image to be deployed on a development server, right? And in order to do that, you have to actually share the image. So it is pushed into a Docker repository, and from there, either people can take it, for example, a tester maybe want to download the image from there and test it locally, or a development server can actually pull it from there. So let's actually just run a container. I'm just gonna say docker run, the image name, obviously, and a tag like this. And in this case, I'm not going to specify any other options because we just want to see what's going on inside of the container. So I'm just going to run it. Okay, so the problem is that it can't find the server.js file, which is actually logical because we are not telling it to look in the correct directory. So since we're copying all the resources in this home/home/app directory, server.js is going to be there as well. And this is another topic. Whenever you adjust a Docker file, you have to rebuild an image because the old image cannot be overwritten, so to say. So what I'm going to do now is actually I'm going to delete the one that I built. So I'm going to actually take the image. This is how you delete an image. But I can delete it because as it says, the Docker is used by a stopped container. So if I do docker ps -a, actually let's grep to my app like this. I have to first delete the container. So this is how you delete a container. It's docker rm. And once I've deleted the container, I can delete an image. So the image deletion is rmi, like this. So if I do images now, I see my image isn't there. Okay, so we've modified the Docker file. So let's rebuild it now. So docker build again. And let's see, the image is here. So let's start it again. So it's my app 1.0 and let's run it. And as you see, the problem is fixed, app listening on port 3000. So our app is running. So this one here, my app 1.0. First of all, we can see the logs here, like this. We see that the app is listening on port 3000. We know everything is cool. To actually just get a little bit more insight, let's enter the containers, or let's get the terminal the command line terminal of the container and look around there. So I'm going to say docker exec interactive terminal. I'm going to specify the container ID in bash like this. And since bin bash doesn't work, we can actually try shell. So this is something you will also encounter because some containers do not have bash installed, so we'll have to connect using bin sh. So one of them has to work always. So let's see in which directory we are. So we are in the root directory and we see our virtual file system there. And as you see, the cursor changed as well. So that means we're inside of a container. So now let's actually check some of the stuff. So first of all, we specified some environmental variables here in the Docker file. And this means that these environmental variables have to be set inside the Docker environment. So if we do env, we actually see the MongoDB username, this one here, and MongoDB password are set. And there are some other environmental variables automatically set. We don't care about them. So another thing we can check is this directory, because remember, because with this line, we actually created this /home/app directory. So let's see /home/app. And as you can see, the directory was created. And with the next line, we copied everything in the current folder. So if we actually go and see reveal in Finder. So this is where the Docker file resides. So basically we copied everything that is inside of this directory. So all of this into the container. Now, we don't actually need to have Dockerfile and Docker Compose and this other stuff in here, because the only thing we need are the JavaScript files, or if we build a JavaScript application artifact, just the artifact. So let's go ahead and improve that. So what I'm going to do is I'm going to create an app directory, and I'm going to copy just the files that I'm going to need for starting an application inside of a container. So I'm going to take those and the images as well. So all these are just external ones. We don't need them there. And images, the index.html file, package.json, server.js, and the node modules are inside of app. So what we can do now is, instead of copying the whole directory where the Docker file is, I just want to copy all the contents of app folder. So what I'm going to do is I'm going to say copy all the app contents. And again, because we modified a Docker file, we need to recreate the image. In order to leave the Docker container terminal, you can actually exit. So now we are on the host again. So if I do Docker images, again, I have to first delete the container and then image. But in order to delete the container, I have to first stop it. So now I can remove the container. And now I can actually remove the image that the container was based on. And let's check again. So let's execute that build command again. So now that we have the image built, let's actually run it. So I'm going to say my app 1.0. And of course, I could have executed with a -d in a detached mode. It doesn't matter now. And if I do docker ps, I see my image container running. And now let's actually enter the container again. So it. And as we learned, it was in sh. And again, we're going to see the home app. And here we just have the contents of app directory. So no unnecessary Docker file, Docker Compose, etc. files, which is actually how it's supposed to be. Or as I said, because I just had a couple of files here, I copied all of them. But usually if you have this huge application, you would want to compress them and package them into an artifact and then copy that artifact into a Docker image container. Okay, but as I said, this was just for demonstration purposes, because I just wanted to show you how you can actually start it as a container and how it actually look inside. And in this case, we improved a couple of things, but usually we would start this container from a Docker Compose as well, together with all the other Docker images that the application uses. So in this video, we're gonna create a private repository for Docker images on AWS ECR. There are many more options for Docker registries, among them Nexus and DigitalOcean. So we're gonna see how to create a registry there, build and tag an image so that we can push them into that repository. And in order to push the images into a private repository, you first have to log into that repository. So let's see how it all works. So the first step is to actually create a private repository for Docker. It's also called Docker registry. In this case, we're going to do it on AWS. So let's see. So I already have an account on AWS. So the service that we're going to use is called Elastic Container Registry. So ECR, Docker Container Registry. And because I don't have a repository there yet, I am presented with this screen. So in order to create a repository, click on Get Started. And here we have a repository name. And we're actually going to name it the name of the application that we have. So I'm actually going to name it my app. This is the domain of the registry from AWS. And this is the repository name, which is the same as my image name. And don't worry about the other stuff right now and just create a repository. It's as simple as that. Now, one thing I think specific to Amazon Container Service is that here you create a Docker repository per image. So you don't have a repository where you can actually push multiple images of different applications, but rather for each image you have its own repository. And you go inside of the repository, here it's empty now, but what you store in a repository are the different tags or different versions of the same image. So this is how the Amazon Container Service actually works. There are other Docker registries that work differently. For example, you create a repository and you can just throw all of your container images inside of that one repository. So I think this is more or less specific for AWS. So anyways, we have a repository which is called my app. And let's actually see how we can push the image that we have locally. So actually check that once more. So we want to push this image here into that repository. So how do we do that? If you click on this one, the view push commands will be highlighted. This is different for each registry, but basically what you need to do in order to push an image into a repository are two things. One, you have to log in into the private repository because you have to authenticate yourself. So if you're pushing from your local laptop or local environment, you have to tell that private repository, hey, I have access to it. This is my credentials. If a Docker image is built and pushed from a Jenkins server, then you have to give Jenkins credentials to log in into the repository. So Docker login is always the first step that you need to do. So here, AWS actually provides a Docker login command for AWS. So it doesn't say Docker login, but in the background it uses one. So I'm going to execute this login command for AWS Docker repository. So in the background, it uses actually Docker login to authenticate. So in order to be able to execute this, you need to have AWS command line interface and the credentials configured for it. So if you don't, I'm going to put a link to the guide of how to do that in the description. I have configured both of them so I can execute this command. And I should be logged in successfully to the Docker repository. So now I have authenticated myself to the Docker repository here. So I'm able to push the image that I have locally to that repository. But before I do that, there is one step I need to do. So I've already built my image, so that's fine. And now I have to tag my image. And if this command here looks a little bit too complicated for you or too strange, let's actually go and look at image naming concepts in Docker repositories. So this is the naming in Docker registries. This is how it works. The first part of the image name, the image full name, is the registry domain. So that is the host, port, etc. / repository or image name and the tag. Now you may be wondering, every time we were pulling an image out of Docker Hub, we actually never had this complex long name of the image, right? So when we were pulling an image, it looked like this, Docker pull Mongo 4.2. The thing is, with Docker Hub, we're actually able to pull an image with a shorthand without having to specify a registry domain. But this command here is actually a shorthand for this command. What actually gets executed in the background when we say docker pull mongo is docker pull the registry domain. So docker.io/library is a registry domain. Then you have the image name and then you have the tag. So because we were working with Docker Hub, we were able to use a shortcut, so to say. In the private registries, we can't just skip that part because there's no default configuration for it. So in our case, in AWS ECR, what we're gonna do is we're gonna execute docker pull the full registry domain of the repository. This is what we're gonna see here, and a tag. And this is how AWS just generates the Docker registry name. That's why we see this long image name with the tag here. And we have to tag our image like this. So let's go back and take a look at our images, our image that we built again. And under the repository, it says my app. Now, the problem is we can just push an image with this name, because when we say docker push my app like this, Docker wouldn't know to which repository we're trying to push. By default, it will actually assume we're trying to push to Docker Hub, but it's not gonna work, obviously, because we want to push it to AWS. So in order to tell Docker, you know what, I want this image to be pushed to AWS repository with the name my app, we have to tag the image. So we have to include that information in the name of the image. And that is why we have to tag the image. Tag basically means that we are renaming our image to include the repository domain or the address and the name. Okay? And AWS already gives us the command that we can execute. We want to use the specific version. So I'm gonna use 1.0 in both. So what this is gonna do is it's gonna rename. This is what tag does. My app 1.0, this is what we have locally. This is what the name is, to this one here. So let's execute that and let's see what the outcome is. And as you see, it took the image that we had, it made a copy and renamed it into this one. So these two are identical images, they're just called in a different way. And now, when we go back, we see the docker push command. So basically this thing here is the same as docker push and name of the image and the tag. So this push command will tell Docker, you know what, I want you to take the image with tag 1.0 and push it into a repository at this address. So when I execute this command, see, the push command will actually push those layers of the Docker image one by one. This is the same thing as when we're pulling it. We also pulled the images layer by layer, and this is what happens in the reverse direction when we push it. So this is also going to take a little bit. Great. So the push command was complete, and we should be able to see that image in the AWS repository now. So if I go inside, see, I have the image tag with 1.0. This is our tag here. And push the time, the digest, which is the unique hash of that image, and the image URI, which is again the name of the image using the repository address, image name or repository name in this case, and the tag. So now let's say I made some changes in the Docker file. You know, let's say I renamed this home /home/app to node app, like this. Or what could also lead to need to recreate an image is obviously when I change something in the code, right? So, you know, let's say I were to delete this line because I don't want the console log to be in my code. And now I have a different version of the application where I have changes in the application. So now I want to have those changes in the new Docker image. So now let's build a new Docker image out of it. So Docker build, let's call it my app with a version 1.1 and a path to a Docker file. And now I have a second image, which is called my app with version 1.1. So now again, because I want to push this to a repository, I have to rename it to include the repository address inside of it. So I'm going to do docker tag. The first parameter is the image that I want to rename. And the second one is the name of that image, a new name. So it's going to be the same as the previous one because the repository name and the address is the same. Remember, we have one repository for one image, but for different versions. So we're building a version 1.1, so it should end up in the same repository. So now here we have 1.1, and if I tag that and images, I have a second image here. So I'm gonna copy that and I'm gonna do docker build. And do not forget the tag, it's important because it's part of the complete name. Sorry, it's docker push. And now some of the layers that I already pushed are there. Only the ones that changed are being repushed, so to say. And also note that I just have to do docker login once at the beginning, and then I can pull and push images from this repository as many times as I want. So docker login is done once. So now that is complete. Let's actually reload this. So my repository now has 2 versions. So this is pretty practical if you are, for example, testing with different versions and you want to have a history of those image tags if you want to, for example, test a previous version. And I think in AWS, each repository has a capacity of holding up to 1,000 image versions. So for example, my app here can have 1,000 different tags of the same image. Okay, so now again, to compare it to the initial diagram that we saw for this complete flow, let's actually switch back to it quickly. So here what we did is basically simulate how Jenkins would push an image to a Docker repository. So whatever we did on our laptop will be the same commands executed on a Docker on the Jenkins server. And again, Jenkins user or Jenkins server user has to have credentials to the Docker repository to execute Docker login. Depending on the registry or repository, configuration will look different, and Jenkins needs to tag the image and then push it to the repository. And this is how it's done. And the next step, of course, we need to use that image that is lying now in the repository, and we're gonna see how it's pulled from that repository. And again, we're gonna do it on the local environment, but it's the same thing that a development server or any other environment will actually execute. So in this video, we're going to see how to deploy an application that we built into a Docker image. So after you package your application in a Docker image and save it in the private repository, you need to somehow deploy it on a development server or integration server or whatever other environment. And we're going to use Docker Compose to deploy that application. So let's imagine we have logged into a development server and we want to run our image that we just pushed the repository, so our myapp image, and the MongoDB image, both the database and the Mongo Express, on the development server. So the myapp image will be pulled from private repository of AWS, and the two Mongo containers will be pulled from the Docker Hub. So let's see actually how that would work. So usually, again, you have developed your application, you're done with it, and you have created your own Docker image, right? Now, in order to start an application on a development server, you would need all the containers that make up that application environment. Okay, so we have MongoDB and Mongo Express already. So what we are going to do is here we're going to add a new container in the list, which is going to be our own image. So let's go ahead and copy the image from our repository. So let's actually use the 1.0. So again, remember we said that this image name is a shortcut for having a docker.io.library/Mongo with like a specific version. So instead of that, because we are pulling these images from a Docker Hub, we can actually skip that repository domain in front of the images. But here, because we're pulling it from a private repository, so if we were to specify our image like this, Docker will think that our image resides on Docker Hub, so we try to pull it from Docker Hub, and of course it won't find it because we have to tell Docker, go and look at this repository with this repository name and this tag. And of course, in order to be able to pull this image, or the Docker Compose to be able to pull this image, the environment where you're executing this Docker Compose file has to be logged into a Docker repository. So here, as the development server has to pull the image from the repository, what we would need to do on the development server is actually do a Docker login before we execute the Docker Compose. And obviously you don't need a Docker login for Docker Hub. Those Mongo images will be pulled freely. Okay, so the next thing that we have to configure are the ports, because obviously we want to open the ports. If we go back, we see that our application runs on port 3000. So the port of the container, or where the container is listening on, is 3000. And here we can open the port on the host machine. So it's going to be 3000 mapped to 3000. We have actually the environment variables inside of the Docker file, but obviously we could have configured them in the Docker Compose, just like this. So it's an alternative. So this will be a complete Docker Compose file that will be used on the development server to deploy all the applications inside. So again, if we're trying to simulate a development server, the first step will be to do the Docker login. In this case, you have this own command for logging into the AWS repository, which I have done already in this terminal. So the next step is to have the Docker Compose file available on this development server, because we have to execute the Docker Compose file. Because we're simulating here, the way I would do it is I'm going to create a Mongo YAML file in the current directory where I am. I'm going to copy this and save. So now I have my Mongo YAML file, and now we can start all three containers using Docker Compose command. -f up. And here we see that app started on 3000 and MongoDB and Express started as well. So let's check again now. And here we saw that database is lost every time we recreate a container. And of course, that's not good. And we're going to learn how to preserve the database data between the container restarts using Docker volumes in the later tutorials, because this is not an ideal state. Okay, so now that we have a database in a collection, let's actually refresh, and our application works as well. Let's check. Awesome. So our application works. Let's refresh this one as well. And there is actually one thing that I needed to change in the code to connect Node.js with MongoDB. So let's actually go and look at that. These are my handlers in Node.js where I connect to the MongoDB database. So the URIs are the same. And what I changed here is that it was a local host before. So instead of local host, I changed it to MongoDB, because this actually is a name of the container or of the service that we specify here. So this actually leads back to the Docker network, and how Docker Compose takes care of it is that in the URI, or when I connect one application in a Docker container with another one in another Docker container, I don't have to use this local host anymore. Actually, I wouldn't even need to use the port even, because I have all that information, so the host name and the port number, in that configuration. So my application will be able to connect to MongoDB using the service name. And because of that, you don't have to specify here a local host and the port number, which is actually even more advantage when you consider using Docker containers to run all of your applications, because it makes the connectivity between them even more easier. And that actually concludes this diagram that we saw previously. We have gone through all of the steps where we saw how to develop a JavaScript application locally with Docker containers. Then we saw how to build them into an image, just like a continuous integration build will do it. Then we pushed it into a private repository, and we simulated a development server where we pulled the image from private repository and the other images from the Docker Hub, where we started the whole application setup with our own application and the two Mongo applications using a Docker Compose, which is how you would deploy an application on a dev server. So that now testers or other developers will be able to access the development server and actually try out the application that you just deployed. Or you can also use it for demos. So in this video, we're going to learn about Docker volumes. In a nutshell, Docker volumes are used for data persistence in Docker. So for example, if you have databases or other stateful applications, you would want to use Docker volumes for that. So what are the specific use cases when you need Docker volumes? So a container runs on a host. Let's say we have a database container, and a container has a virtual file system where the data is usually stored. But here there is no persistence. So if I were to remove the container or stop it and restart the container, then the data in this virtual file system is gone and it starts from a fresh state, which is obviously not very practical because I want to save the changes that my application is making in the database. And that's where I need Docker volumes. So what are the Docker volumes exactly? So on a host, we have a physical file system, right? And the way volumes work is that we plug the physical file system path, it could be a folder, a directory, and we plug it into the containers file system path. So in simple terms, a directory, a folder on a host file system is mounted into a directory or folder in the virtual file system of Docker. So what happens is that when the container writes to its file system, it gets replicated or automatically written on the host file system directory, and vice versa. So if I were to change something on the host file system, it automatically appears in the container as well. So that's why when a container restarts, even if it starts from a fresh state in its own virtual file system, it gets the data automatically from the host because the data is still there. And that's how data is populated on the startup of a container every time you restart. Now, there are different types of Docker volumes, and so different ways of creating them. Usually the way to create Docker volumes is using docker run command. So in the docker run, there's an option called -v, and this is where we define the connection or the reference between the host directory and the container directory. And this type of volume definition is called a host volume. And the main characteristic of this one is that you decide where on the host file system that reference is made. So which folder on the host file system you mount into the container. So the second type is where you create a volume just by referencing the container directory. So you don't specify which directory on the host should be mounted, but that's taking care of the Docker itself. So that directory is, first of all, automatically created by Docker under the var lib docker volumes. So for each container, there will be a folder generated that gets mounted automatically to the container. And this type of volumes are called anonymous volumes because you don't have a reference to this automatically generated folder. Basically, you just have to know the path. And the third volume type is actually an improvement of the anonymous volumes, and it specifies the name of the folder on the host file system. And the name is up to you. It's just to reference the directory. And that type of volumes are called named volumes. So in this case, compared to anonymous volumes, you can actually reference that volume just by name. So you don't have to know exactly the path. So from these three types, the mostly used one and the one that you should be using in production is actually the named volumes, because there are additional benefits to letting Docker actually manage those volume directories on the host. Now, this showed how to create Docker volumes using docker run commands. But if you're using Docker Compose, it's actually the same. So this actually shows how to use volume definitions in a Docker Compose. And this is pretty much the same as in docker run commands. So we have volumes, attribute, and underneath you define your volume definition, just like you would in this -v option. And here we use a named volume. So db-data will be the name, reference name that you can just think of. It could be anything. And var lib MySQL data is the path in the container. Then you may have some other containers, and at the end, so on the same level as the services, you would actually list all the volumes that you have defined. You define a list of volumes that you want to mount into the containers. So if you were to create volumes for different containers, you would list them all here. And on the container level, then you actually define under which path that specific volume can be mounted. And the benefit of that is that you can actually mount a reference of the same folder on a host to more than one containers. And that would be beneficial if those containers need to share the data. In this case, you would mount the same volume name or reference to two different containers, and you can mount them into different paths inside of the container even. In this video, we are going to look at Docker volumes in practice. And this is a simple Node.js MongoDB application that we're going to attach the volume to so that we don't lose the database data every time we restart the MongoDB container. So let's head over to the console, and I'm going to start the MongoDB with the Docker Compose. So this is how the Docker Compose looks like. We're going to start the MongoDB container and the Mongo Express container so that we have a UI to it. So I'm going to execute the Docker Compose, which is going to start MongoDB and the Mongo Express. So when it started, I'm going to check that Mongo Express is running on port 8080. And here we see just the default databases. So these are just created by default on startup. And we're going to create our own one for the Node.js application. And inside of that database, I'm going to create users collection. So these are the prerequisites, or these are the things that my Node.js application needs. So this one here, in order to connect to the database MyDB, this is what we just created, MyDB, and inside of that to the collection called users. So let's start the application, which is running on port 3000. So here, and this is our app, which when I edit something here, will write the changes to my database. Now, if I were to restart now the MongoDB container, I would lose all this data. So because of that, we're going to use named volumes inside of the Docker Compose file to persist all this data in the MongoDB. So let's head over to the Docker Compose. So the first step is to define what volumes I'm going to be using in any of my containers. And I'm going to do that on the services level. So here, I define the list of all the volumes that I'm going to need in any of my containers. And since we need data persistence for MongoDB, we're going to create a Mongo data volume here. Now, this is going to be the name of the volume reference, but we also need to provide here a driver, local. So the actual storage path that we're going to see later once it's created, is actually created by Docker itself. And this is a kind of an additional information for Docker to create that physical storage on a local file system. So once we have a name reference to a volume defined, we can actually use it in the container. So here, I'm gonna say volumes. And here I will define a mapping between the Mongo data volume that we have on our host, and the second one will be the path inside of the MongoDB container. It has to be the path where MongoDB explicitly persists its data. So for example, if you check it out online, you see that the default path where MongoDB stores its data is data/data/db, and we can actually check that out. So if I say docker ps and go inside the container, it's -it. I can actually see data db, and here is all the data that MongoDB actually holds. But this is, of course, only the container. So when the container restarts, the data get regenerated. So nothing persists here. So this is the path inside of the container, not on my host, that we need to reference in the volumes here. So we're attaching our volume on the host to data/data/db inside of a container. So for example, for MySQL, it's going to be var lib MySQL. For Postgres, it's also going to be var lib PostgreSQL/data. So each database will have its own, so you'd have to actually find the right one. So what this means is that all the data that we just saw here, all of this will be replicated on a container startup on our host, on this persistent volume that we defined here, and vice versa. Meaning when a container restarts, all the data that is here will be replicated inside of that directory inside of a container. So now that we have defined that, let's actually restart the Docker Compose. And restart it. So once we create the data, and I'm going to use the collection, and let's actually change this one. Let's put travel here and update it. So we have the data here. So now that we have the persistent volume defined, if I were to restart all these containers, this data should be persisted. So on the next restart, I should see the database, my DB collection, and the entry here. So let's do that. I'm gonna do down. Great, so let's check. See, the database is here, the collection is here, and the entry has persisted. So now let's actually see where the Docker volumes are located on our local machine. And that actually differs between the operating systems. For example, on a Windows laptop or a computer, the path of the Docker volume will be at program data docker/volumes. The program data Docker folder actually contains all the other container information. So you would see other folders in this Docker directory besides the volumes. On Linux, the path is actually /var lib docker volumes, which is comparable to the Windows path. So this is where the Docker saves all this configuration and the data. And on the Mac, it's also the same one. Inside of this volumes directory, you actually have a list of all the volumes that one or many containers are using. And each volume has its own hash, which has to be unique. And then /_data will actually contain all the files and all the data that is persisted. Let's head over to the command line and actually see the volumes that we persisted for MongoDB. Now, an interesting note here is that if I were to go to this path that I just showed you in the presentation, which is var lib docker, see, there's no such a directory. So that could be a little bit confusing. But the way it works on Mac, specifically on Linux, you would actually have that path directly on your host. But on Mac, it's a little bit different. So basically what happens is that Docker for Mac application seems to actually create a Linux VM in the background and store all the Docker information or Docker data about the containers and the volumes, etc. inside of that VM's storage. So if we execute this command here, so this is actually the physical storage on my laptop that I have where all the data is stored. But if I execute this command, I actually get the terminal of that VM. And inside here, if I look, I have a different virtual file system. And I can find that path that I showed you here. So it's var lib docker. See, so I have all this Docker information here. I have the containers folder and I have volumes folder. So this is the one we need. So that let's actually go to the volumes. And this is a list of volumes that I have created. And this is the one that came from our Docker Compose, right? This is the name of our app. This is what Docker Compose actually takes as the name. We can actually take a look here. So when it's creating these containers, it appends this name as a prefix, and then there is MongoDB. And our volume has the same pattern. It has the prefix, and then MongoData, this is the name that we defined here. So now, if we look inside of that MongoData volume directory, we see that _data. This would be the anonymous volumes. So basically here you don't have a name reference, it's just some random unique ID, but it's the same kind of directory as this one here. The difference being that this one has a name. So it's easier to reference it with a name. So this is anonymous volume, this is a named volume. But the contents will be used in the same way. So here, as you see in this _data, we have all the data that MongoDB uses. So this will be where it gets the default databases and the changes that we make through our application inside. And if I go inside of the container, so remember this volume is attached to MongoDB and is replicated inside of the container under path /data/db. So if we go inside of the container, actually do it here, PS. /db. We'll see actually the same kind of data here. So we have all this index and collection files, just like we did in this one. So now whenever we make changes to our application, for example, we change it to Smith, whatever, and this will make the container update its data, and that will cascade into this volumes directory that we have here. So that on the next startup of a container, when the /data/db is totally empty, it will actually populate this directory with the data from this persistent volume, so that we will see all the data that we created through our application again on startup. And that's how Docker volumes work. In order to end that screen session that we just started, because exit doesn't work in this case somehow, on Mac you can actually click on Control-AK and then just type Y and the session will be closed. So when you do screen ls, you should see actually it's terminating. So now that we have worked with Docker and we have pushed images to a repository, we can actually create a Docker repository on Nexus, and we can push our images to Nexus Docker repository. For that, in the administration and configuration view, where we manage our repositories, we can create a new repository here. And from the list, we're going to choose Docker hosted, because we're going to be pushing our own Docker images to this repository. And we can call it Docker hosted. We'll leave all this configuration for now as is and select my store, blob store, which we created in the Nexus part, and leave the rest as is. And with this, we can create a repository. And if I click inside, here I have the URL of the repository, which we can use to push the images to this repository. Now, in order to start pushing our Docker images to this Docker repository, we first have to log into Nexus using a Nexus user, which has access to Docker hosted repository. And we're going to do that using Docker login command. So the first thing we need to do is create a new role that has a privilege or access to Docker hosted repository, just like we did for Maven repository. So I'm going to create a new role. Let's call it nx docker. Let's use the same name. And here in the list, we have, again, admin prefix is for administrators who are managing and administering this repository. View is for the users. So we are gonna take Docker hosted privilege and assign it to this role and create a role. And we can assign that role to our existing user that already has access to Maven repository. So we're gonna add Docker repository permission to it and save the user. So now this user can be used to access and log in into Nexus using Docker login command. So let's go ahead and do that as well. Now there are a couple of things we need to configure in order to be able to execute Docker login with a Nexus user successfully. The first thing that we need to do in Nexus is go to our Docker hosted repository, and we're gonna edit this field right here, the HTTP. Now the reason for it is that Docker client cannot connect to a path which represents a Docker repository. So we cannot use this as an endpoint for Docker login. The endpoint we can use for Docker login will be an IP address and the port, right? However, this port is where Nexus itself is running, right? So we need a port for Docker repository specifically. So its own individual port where Docker repository will be accessible at. And this is exactly what we can configure right here. And this repository connectors section that you see right here is only available for Docker registry type. You don't have it in Maven and other types, And we're using a not secure connection for Nexus. So we're going to configure the HTTP for our Docker repository. So I'm going to click on this, and here we can set a port which is different from a Nexus port. And let's just take 8083, for example, and we're going to save that change. So now that we have configured this port for our Docker repository, this repository is now accessible at IP address of the server where Nexus is running and the port that we defined here. So if I go back to our droplet where Nexus is running and I do netstat lnpt, here you see this is the Nexus port, and now another port just got opened on that server, on this droplet, for 8083. So we can actually connect to this port in order to talk to Docker repository. Cool. So that's configured. Another thing that we need to do in order to be able to access this port is to open this port on a droplet's firewall configuration. So let's go to DigitalOcean, and in networking firewalls, this is the firewall that is attached to our droplet. We need to open that port, otherwise all the requests from Docker login or Docker other commands from Docker client won't be able to access the port if we're not exposing it. So let's do custom and 8083, save. Now we have opened the port, and that port will allow us to talk to Docker repository. And the final thing we need to configure in Nexus itself is something called a realm. So what happens is that when we do Docker login, we get a token of authentication from Nexus Docker repository for a client, right? And that token will be stored then on my local machine in a file called config.json in the .docker folder in my home directory. And this JSON file will include all the authentications that I have made to all the different Docker repositories. If you haven't logged into a Docker repository ever from your laptop, you won't have this file. The first time you log into any Docker repository, Docker Hub, AWS, Docker repository, or Nexus, this file will be generated with the authenticated token or authentication token inside. And then this token will be used every time you interact with that repository. So if you push images, if you pull images into that repository or from the repository, then this token will be taken from the config.json, right? So we need to configure in Nexus issuing, so to say, of that token. And we can do that in realms. And here you see Docker Bearer token realm, and we're gonna activate it because it's inactive by default. And we're gonna save it. And all the configuration is done in Nexus. However, we still have one configuration to do in the Docker itself. And the reason for that is that Docker by default only allows client requests whenever we execute a command like docker login, docker pull, docker push, all these commands to go to and talk to an HTTPS endpoint, a secure endpoint of a Docker registry. And because we have a not secure registry, so to say, because our Nexus is running on HTTP, we haven't configured it yet, we need to configure Docker client to allow our Docker hosted repository as an insecure registry. So we are telling Docker, look, we know this registry, this is ours, so I want to allow it as an exception, and I'm going to configure that as an insecure registry. The way you do that in a Linux system is by editing a file called daemon.json. This is Docker daemon at this path, and then adding an insecure registries list to that file. However, if you're using a Docker desktop, either for Mac or Windows, you will not have this file locally at any path because Docker desktop actually starts as a virtual machine on your Mac or Windows. So it has its own virtual file system, so to say. And you can access that file system, that virtual file system of Docker Desktop. However, it's a little bit more complicated, and we're gonna do it the easy way. And the easy way will be to go to your Docker Desktop UI. In the preferences here, depending on your Docker version, you will find a tab that allows you to add some additional configuration in a JSON format. In the old Docker, this will be a daemon tab, advanced, and here you can add the configuration. In the new version, this will be Docker engine, and here we have already some configuration. And on the next line, after experimental, we're gonna add this line. So insecure registries, and this is the IP address of Nexus. This is where Nexus is running, and this is the port of Docker repository on Nexus, right? This is what we configured here, because that's where the Docker repository is accessible now. So we're gonna say this is insecure registry. You can provide here a list and apply and restart, and Docker daemon or Docker engine will allow us to send client requests, Docker client requests, to that registry with HTTP. So let's wait for Docker to restart. So Docker is running again, and now we can actually authenticate with Docker, and we can do Docker login. So I'm gonna do Docker login. So in Docker login, we are gonna provide the registry endpoint, the IP address without the protocol here, and port of the repository. And this will ask for your Nexus username, which is authenticated to interact with this repository. And login succeeded. And here you see that this .docker/config.json file got updated. So this file now has the token that Docker repository issued back to our client, so that we don't have to log in every time we execute commands now. So if I did Docker login again, it doesn't ask me for credentials anymore because it has my token, the authentication token. And now that we are logged in to Docker repository, we can actually push images to that repository. So how do we push an image to our Nexus Docker repository? So first we're gonna build an image with this name and a tag. The image is built, and now we will need to retag that image. We need to tag this image, an existing image, to include the address or the name of the repository itself. And as you already learned from the previous videos, when we execute Docker push, we don't specify explicitly the repository where it needs to push to, but rather we implicitly include it in the name of the image itself. So I'm gonna take that image that I just built, and I'm gonna retag it, so to say. And the new tag will include the address, the endpoint of the repository. Again, we need the IP address without the protocol. Port of the repository, 8083. And then we can take the name and version or tag of our existing image. So this becomes part of our new image name. However, it implicitly tells Docker where to push this image to. So if I execute this command, now I will have Docker images. one with the simple tag with my image, and another one including the address of Docker repository. So now we can do docker push using the name, the complete name of the image, and it will know to push this image to this address. And you see different layers are getting pushed. And the image got pushed. Now if you go back to Nexus, let's go to the repositories, Docker hosted, and here you see the image. We can expand it, have the tags, manifests, and some more assets. So here you see this is the component that got pushed, and this component has a bunch of assets which are different layers of Docker. So this is the same tag here that you see right here. So the image and its different layers got actually pushed into the repository. And as I mentioned previously in the Nexus part, in Docker repository, the components and assets are actually handled a little bit differently compared to other repositories. You have the different layers of the image that you see here. They got pushed one after another. They actually get treated and handled as assets, and these assets or layers can be used by other Docker images as well. And that's why this type of structuring. So we have uploaded our image to Docker repository. We can also pull the images from there because we have authenticated ourselves, and the authentication token is locally stored, so we don't have to log in to the repository again. And we can also fetch the available Docker images from the repository using Nexus API. So we can do a curl with Nexus user and password. This is the endpoint, components, and repository will be Docker hosted. And if I execute this, I'm going to have the item. We just have one item there. This is the ID and its assets. In this case, also one asset listed here in a JSON format. So this way you can retrieve the Docker images from endpoint with some information. So in the Nexus module, you learned how to install Nexus on a DigitalOcean droplet, right? When we set it up, we had to do all of these steps in order to install and run Nexus on a DigitalOcean virtual server, right? We had to install Java, then we had to download Nexus package, we had to untar it, we had to create a Nexus user on an operating system, we had to give it permission to the Nexus directories. We had to configure Nexus to run with Nexus user, and then we were able to start Nexus repository manager. Now, an easier way to install Nexus and to get started with it much faster is actually to install it as a Docker container. And that's what we're going to do in this video. We're going to install Nexus repository manager as a Docker container on a DigitalOcean droplet. So let's go to DigitalOcean. We have one droplet already that runs Nexus. So we're going to create a new one. Let's create a fresh new droplet. Let's choose this plane right here, the region, and create droplet. This is going to be the same droplet, same type, also in this case, same resources. And once it's ready, we can connect to it using this IP address. And let's actually change the name of our droplet because right now they are called the same. So let's call it Docker Nexus. And now we can connect to this droplet. However, first we will need to configure a firewall so that we can access port 22. So in the firewall configuration, we're going to add our droplet. We called it Docker Nexus. And now our droplet has firewall configured. And we can access it on port 22. And let's do that. So SSH root address, and we are on the server. Now, again, we don't have anything installed yet. And for this deployment, we actually only need Docker to be installed on this server. We don't need Java because we're not running Java application directly on the server. We are gonna run Docker image, Docker container. So we're gonna need Docker runtime. So I'm just gonna type Docker here, and then we're gonna first update the package manager, and then we can actually install the latest version. And Docker is installed. We have commands available, Docker is running. So now we can just go ahead and find a Nexus official image that we're gonna start on the server. So on Docker Hub, we can look for Nexus 3. And here you see this is the official one from Sonatype, and this is the image that we need. So let's take a quick look at documentation of this image. Here we see how to run, which ports are open, etc. And when we start Nexus, we need one thing to configure for Docker, and that is storage. So we want Nexus obviously to persist all of its data on the server itself, on the host. So because of that, we are gonna need to configure volume for it. Because otherwise, if the container died and we had to create a new one, then all the Nexus data will be gone. But we want to persist it on the server, just like it was before. So we're gonna run it with mounted volume. So first we're gonna create a Docker volume. Let's actually use those commands and copy them. So volume create Nexus data. So Docker will create volume for us with this name, and then we can execute Docker run command to start Nexus container. So this will run the container in the background in a detached mode. This will allocate the port. So it will run on 8081 on the server's port, because we know the application is running on this port already inside the container. Here we just give a container name, otherwise it will just be auto-generated by Docker. And this is where we configure a volume. We created a named volume here that has some automatically generated path somewhere on the file system that Docker is managing. And we are gonna mount that path by referencing it using this name inside the Docker container in /nexus data. And this is just an image name. So we're gonna run this. Docker will pull the image, and Nexus just started. We can actually see whether the port is open. Let's install the netstat for debugging. So netstat is installed. Let's execute it again. And here you see the port is open, so we can actually send request to this port. And this will then forward it to Docker container. Let's also do Docker PS. And here you see our container is running, the port is open. And now if I go back to Droplet, let's take the IP address and the port. We're gonna see Nexus repository UI. So we deployed Nexus as a Docker image on a server. This actually was much faster than deployment without Docker, because we only needed to install Docker runtime, and then we could start the image pretty easily. Now, another thing that we did in the first installation was we created an operating system user, a Linux user, to run Nexus, because it is a bad practice to run services with a root user. So if we go into the Docker container, let's actually clean this up and do Docker PS, take the ID, And let's actually enter its shell or bash. And here you see a $sign means that it is running as a non-root user. And the user that is running inside the container is Nexus. So the user creation and starting Nexus with a Nexus user was also done out of the box. Inside the image, we didn't have to configure any of those. And if you need to check this kind of information in the image itself, if it's not in the documentation, you can usually look in the tags and just open one of those tags. And here you have the image layers. This is a view of a Docker file of how the Docker image was created. And here you see all the information. And at the bottom, we have user Nexus. And this is also good practice to run Docker images or Docker containers with their own service user. So if you have a container that runs as a root inside, is not very preferable. So this setup was pretty easy. We have another Nexus running where installation and deployment was much faster than the first time using Docker. And as we mounted a volume into a Nexus container, the data should be persisted on a server, on the server locally. So even if we remove the container, the data will still be there, which is also what we need because we don't want to lose this data. And if you want to see the actual location of where this data is stored on your server's file system, you can do docker volume ls. This will give you the list of all the volumes that you have configured. And this is the name of the volume. This is a named volume, so we have given it a name. If it's an anonymous, it's going to have a long hash as a name. So docker inspect name of the volume will give us some more information about the volume, including the actual physical path on the server where that volume is located. So if we look inside that path, we see all the data of Nexus stored right here. So in the first installation, we saw that Nexus application was stored in a separate folder that included Nexus executables or binaries to start the application and a separate folder for data. And this is basically a separate folder where the data, the Nexus data, configurations, etc. is mounted. So this is this Sonatype work volume mount, so to say. And you will need this location to do backups as well as maybe look up a password or some other information here for debugging, etc. to have some information. Alternatively, you can also look inside the Docker container file system because all of these files are mounted into Docker container, so this file should be there as well. We can check that very quickly. Let's do docker exec again. And if I do ls here, we mounted the volume into this path right here, /nexus data. So if I look inside Nexus data, inside the container, because we're inside, I see the replication of this data because they are connected. So you can check this information either in the container itself or on the server like this.